If you can recall our last video on enzymes kinetics 1, we discussed the Michaelis-Menten kinetics graph in great detail. So basically in the Michaelis-Menten graph, we plot the substrate concentration on the x-axis and the velocity of the enzyme activity on the y-axis. And the two things that we can determine from the graph is the Vmax, which is the maximum velocity of the reaction that can occur in the presence of the enzyme. And the second thing is the Michaelis constant, Km. We go to the point along the y-axis, which is Vmax divided by 2, half of the Vmax. And whatever substrate concentration correlates with that point is the Michaelis constant, Km. So now let's look at what happens if an inhibitor is added to this reaction. First, we'll try and add a competitive inhibitor. This would occupy some binding sites of the substrate. But if enough substrate was added, the inhibition may be overcome, and you can still achieve Vmax. However, because of the presence of inhibitors, Km is shifted to the right. What that means is that in the presence of a competitive inhibitor, the Vmax is the same, but the Km becomes higher. Now let's talk about non-competitive inhibitors. So this is like destroying the enzymes altogether. So in this graph, we can see the Vmax falls because some enzymes are simply not working anymore. So what's interesting is that the Vmax is changed. It has become lower, but the Km, the Michaelis constant, remains the same. This means that there is just less functional enzyme around because of the non-competitive inhibitors. So now let's look at this on the Lineweaver-Burk plot, which we also talked about in great detail in our Kinetics 1 video. So we plot 1 over S on the x-axis and 1 over V on the y-axis, and a straight line is then achieved. And the point where it crosses the y-axis is known as 1 over Vmax, and where the line crosses on the x-axis is known as minus 1 over Km. So what changes when you add a competitive inhibitor? This is relatively easy to remember when you know and realize what component changes and what remains the same, as we mentioned earlier. So when you add a competitive inhibitor, the Vmax does not change. So the point where the line crosses the y-axis does not change. And the minus 1 over Km moves closer to 0. Now let's see when you add a non-competitive inhibitor. Now in this case, the Km constant does not change. So the point where the line crosses the x-axis remains the same. The only thing that does change is the Vmax. It decreases. So 1 over Vmax goes up on the y-axis. Remember that the Lineweaver-Burk plot is an inverted form of the Michaelis-Menten graph. So again, if the Vmax decreases, 1 over Vmax goes up on the y-axis. Okay guys, so in this section, we're going to quickly summarize everything that we've learned so far about inhibitors and also talk about some commonly found drugs which are inhibitors. So, any substance that can decrease the velocity of an enzyme-catalyzed reaction is considered to be an inhibitor. And inhibitors can be reversible or irreversible. Irreversible inhibitors bind to enzymes through covalent bonds, while reversible inhibitors bind to enzymes through non-covalent bonds, forming an enzyme inhibitor complex. Reversible inhibitors can be further divided into competitive and non-competitive inhibitors. Competitive inhibition is a type of inhibition that occurs when inhibitors bind reversibly to the same site that the substrate would normally occupy, and therefore it competes with the substrate to bind to the enzyme for the active site. The effect on Vmax is that it can be reversed by increasing the concentration of substrate. The Vmax is unchanged in the presence of a competitive inhibitor. The effect on the Michaelis constant Km is there is an increase in the apparent Km for a given substrate. This means that in the presence of a competitive inhibitor, more substrate is needed to achieve half the Vmax. And a good example of a competitive inhibitor are statin drugs. Statin drugs are cholesterol-lowering agents that competitively inhibit the rate-limiting step in cholesterol biosynthesis. Statins, such as atorvastatin and pravastatin, are structural analogs of the natural substrate for this enzyme, and they compete effectively to inhibit the HMG-CoA reductase, and by doing so, they inhibit the de novo cholesterol synthesis. In non-competitive inhibition, this occurs when the inhibitor and substrate bind at different sites on the enzyme. The non-competitive inhibitor can bind either free enzyme or the enzyme-substrate complex, thereby preventing the reaction from occurring altogether. The effect on Vmax is that the effects on the non-competitive inhibitors cannot be overcome by increasing the concentration of the substrate. Therefore, a non-competitive inhibitor decreases the apparent Vmax of the reaction. The effect on the Michaelis constant Km is that because the non-competitive inhibitors do not interfere with the binding site of the substrate to the enzyme, therefore the enzyme shows the same Km. So Km is unchanged in the presence of a non-competitive inhibitor. Now in medical school, there are a few examples of drugs that are enzyme inhibitors that are widely known, such as beta-lactam antibiotics, such as penicillin and amoxicillin, which basically act by inhibiting enzymes involved in the bacterial cell wall synthesis. Another example is an angiotensin-converting enzyme, or ACE inhibitors. They lower the blood pressure by blocking plasma angiotensin-converting enzyme that cleaves angiotensin 1 to form the potent vasoconstrictor angiotensin 2. And another example is aspirin, a non-prescription drug which irreversibly inhibits prostaglandins and thromboxane synthesis by inhibiting cyclooxygenase. So that was all the things you need to know about enzyme inhibitors. We hope you enjoyed this video, and we'll see you next time on sqadia.com.